Okay, what I'm going to do right now is section 6.6 and 6.7 exercise problems. Okay, wait a second. Okay, 자, 준비됐으면 I'm going to start solving these problems. Evaluate each expression to the nearest thousandth. If the expression is undefined, write undefined. 자, 여기 몇 개 해보자. e to the sixth, e to the sixth. evaluate 하라 그랬으니까 이거는 계산기에 넣어야겠지 그냥. 뭐 e to the sixth power 뭐 해주면 let me use my calculator. e to the power of 6. It's like 403. 0.429. About this much. Okay. 이건 전부 다 calculator input 하면 되는 거니까 어려울 건 없어. 그냥 다 집어넣고. ln3. So there's a ln button on the calculator. There's like log and ln. As I said, this is called natural log. And log is, if you don't have any base written down here, that means it's a common log. Common log means the base is 10. Okay, so 10 is kind of hidden here. Okay, so for ln3, you just press ln button and then 3, then you get 1.099. Okay, 26 ln 0.004 is equal to negative 5.521. Okay, as you can see, the base of natural log is basically e. E is approximately equal to 2.718. Okay, you have like bunch of numbers after this one. So this is an irrational number. So anyway, whenever you have a log, remember if we have log base 2, and if this number is 2, that evaluates to 1. Okay, I'm gonna show you two more. If you have log base 2 and 4 here, and then log base 2 and let's say 1. One more. Log base 2 and 1/2. Okay, starting from here, these two numbers, base and the number inside log, are basically same. In this case, you get the answer of 1 here. But when this number inside the log is greater than the base, you get a number that is greater than 1. So answer for this one is 2. Okay, now for this one, here is the base 2, but the number inside log is 1, which is smaller than the base. Then this answer is less than 1, so you get 0. 2 to the power of 0 is 1. Okay, again, this number is less than this base. But in this case, you get negative number, negative 1. So one thing that you have to notice is that if this base and this number is same, 1, whenever this number is less than the base, you get a number that is less than 1. And if this number is greater than the base, you get a number that is greater than 1. So same thing applies here. This is ln 3, okay? Look at this. 3, the base of natural log is e, which is 2.7, okay? But you have the number that is greater than the base. So you ended up with a number that is greater than 1 here. And this number, for number 26, 0.004 is way smaller compared with what? The base of e, which is 2.7. So you ended up with a number that is less than 1, and in this case it's even what? It went into a negative territory, negative 5.5. Okay, it's a very small number here. All right. So looking at 27, this number 0.994 is less than 2.7, so you'll get a number that is less than 1. Okay, so you know from the start that it's going to be less than 1. So if you get a number that is greater than 1, you did something wrong. Okay, 0.994 is negative 0.006. So what this means is that, okay, if this number is less than 1, you end up with a number that is negative. Okay? When this is exactly 1, your answer is 0. But if this number is less than 1, you end up with a negative number. Same thing here, ln 1 over 5. 1 over 5 is less than 1, so your answer will be a negative number. Okay? So ln 1 over 5 is equal to negative 1.609. All right, 29. Square root of 5 is, it's greater than 1. It's 2 point something, right? It's 2.3, okay? Square root of 5 is basically 2.236, but that, okay, this is 2.236, but this number is less than 2.718, so you're going to get a number that is what? Less than 1. So ln, so let me see, ln square root of 5 is exactly equal to 0.8047189562, but it's what? We have to round it to the nearest thousandth, so it's 0.805. Okay, that's approximately equal to this much. All right. For number 30, it says ln negative 2. Can we have a negative number inside the log? Absolutely not, okay? So this is undefined. You cannot have 0 either. 0 or negative number, no good, okay? So this is also undefined. All right, let me move over to the next block here. Write the expressions in ascending order. So we have to compare all these 4 numbers. The smallest number out of all these is ln 2, because this 2 is less than e, so you're going to end up with a number that is less than 1. So ln 2 is the smallest number. And then ln 5, this 5 is greater than 2.7. So this is obviously what? Greater than 1. But how about e squared? E squared is basically e times e. It's like 2.7 times 2.7. So you'll get a number that is between 4 and 9. Okay, 2.7 times 2.7, it's like what? It's 7.29. But ln 5 is not quite this much, because if you have ln, let's say, e squared here, that evaluates 2, because this base is e. So if you, okay, the e, let's say e is hidden here. So if you raise this to the power of 2, you get this number. So e squared is 7.29, but you have, I mean, there's this 5 is obviously less than 7.29. So if you compare ln e squared and ln 5, you know that this number is less than this number, e squared. So you know that ln 5 is what? Way less than e squared. So the next number is ln 5. ln 5 is actually, let me see, it's like 1.6. The next number is obviously e squared. The next number is e to the fifth. Okay, so this would be the answer for 32. Okay, do the rest by yourself. All right, next block. State whether each equation is always true, sometimes true, or never true. Let's look at number 36. So if you apply the basic exponent rules, since you have the same base e, you can simplify this thing to e to the power of 5x plus 3. And is this equal to e to the 15x? Let's see. Okay. For them to be equal to each other, this exponent has to be the same. So 5x plus 3 is equal to 15x. So this comes down to 10x is equal to 3. So x is 3 over 10. So what this means is that these two expressions are basically same only when x is equal to 3 over 10. If you plug in any number other than 3 over 10, they're not going to be the same anymore. So this means it's sometimes true, because it's true when x is equal to 3 over 10, but false otherwise. Okay. Okay, 37, this thingy right there, since you have this something, the parenthesis, to the power of 3, the basic exponent rules say that you multiply these two together. So this comes down to e to the 12x. And of course, this is e to the 12 equal to e to the 12x. Okay. Okay, so you can put in any number for x, and you find that these two expressions are basically the same. So this is always true. Okay, I think you can do 38. I also think that you can do 39. Okay, try for yourself. All right, let me go over to the next block. Simplify each expression. Okay, remember this. One of the properties of the log is that if you have a base a, and if you raise it to the power of log of something, but in this case, the base of this log is also a, and you have number b here, then everything cancels out, and then it comes down to just b. Why is this impossible? You can confirm that this is legit or not. Okay, this is an exponential form basically. This is an exponential form. So this just says a to the power of this much is equal to b. So you can convert this into a logarithmic form, log form, okay? So if you convert it to log form, what do you have to do? Just write down log. What is the base? Base is a. So if you raise a to power of what? This rectangle, okay? Then you get a number b, okay? So what is that rectangle? Inside the rectangle, you got log base a and b, okay? So this is basically same expressions on the left hand side and right hand side. So it's totally legit, okay? So whenever you see a power, okay, log power, and check the base. If this base and this base are same, just get rid of everything else and then just write down b. Okay, using that method, if you look at 40, here's a base e to to the power of log, but it's natural log, so its base is e. So we got the same base here, so this comes down to just 2. Same thing in 41 too. What would be your answer? You guess. I mean, it's very simple. Okay, let me do 42. Okay, now I got something a little bit different here. E to the power of 3 ln 2. When I showed you this property, this one did not have any number in front of this log. Now it has a number in front of this natural log. So what this means is that you have to get rid of this number so that you can use this property right there, okay? So what can I do with this number? There was another property of the log where it says, okay, we have log base A and then B, and this B has some power on it, n. Then we can bring that number in front of this log. So we can write it down as n log base A B. Okay, I mean, these two are basically equal to each other, so you can go from left-hand side to the right-hand side. That means that, what that means is that you can go from the right-hand side to the left-hand side. So you take this number and bring it back here as the exponent of 2. So this can be rewritten as e to the power of ln 2 to the power of 3. Now, it's got base e. This natural log has base e, so it's not there, but here's e, okay? So they are same. So you get rid of everything else except 2 cubed. So this is your answer, which is 8, okay? So that is 8. You do the same thing for 43. Okay, 44 is basically uses this property, okay? So if take this number, bring it in front of this log, then that's 3 ln e. ln e is what? It's just 1. So that's 3 times 1. So the answer is 3. You can do 45, you can do 46, you can do 47. So try them by yourself, okay? Next block. Write an equivalent exponential or logarithmic equation. Okay, this is exponential form. Let's convert it to a logarithmic form, okay? So the base is e, so you have to use ln. ln 30 is equal to x. So that's e to the power of the x is 30, okay? You can do 49, do it yourself. Okay, how about this? This is, okay, ln, so base e to the power of what? This thing, 0.69, then you'll get 2. Then you get approximately equal to 2, okay? Okay, I think you can do 51. I think you can do also 52 and 53, but I'm going to go over 52. When converting from exponential form to logarithmic form, you can use this method by memorizing how to take the exponent, base, and things like that. But there is another simpler way of doing this, which is this. If you have base e here, you're going to use ln, right? So apply log, natural log, on the left-hand side and right-hand side all together because they are basically same, okay? So do the equal treatment to the left-hand side and the right-hand side. ln e to the power of 1 over 3 is approximately equal to ln 1.40. So I apply the natural log on both sides. Then this number, the power, can be brought in front of this log. So you end up with 1 over 3 ln e is approximately equal to ln 1.40. Now, what is ln e? ln e is just 1, okay? So left hand side is basically 1 over 3 times 1, so that's 1 over 3. So what this means is that ln 1.40 is approximately equal to 1 over 3. Okay, so you can use this method of applying log to both sides, okay, if you have an exponential form. All right, so try this method for 53, okay? You can easily do it. Let's move to the next block. Solve each equation for x by using the natural logarithm function. Round your answer to the nearest hundredth. Okay, this is exponential form. So what you can do is, as we've seen just now, you can apply, it says using natural log. So it doesn't matter what kind of base you have. Even though here base is 35, you can still use natural log. So I'll show you what I mean. So you can apply natural log on both sides. ln 35 to the power of x is equal to ln 30. Okay, I'm doing 54. Now, this x is an exponent of 35, so let me bring it in front of this ln. So it becomes x ln 35. And this is equal to ln 30. Our goal is to find out what x is. So I'll leave x here, and I'm dividing each side by ln 35. Then you'll end up with ln 30 over ln 35. So what can you do here? You can directly input that expression into your calculator. Or if you want to, you don't have to do it, but if you want to, using change of base formula, remember change of base? Change of base is log b with base a can be written as, you can use any base here, you can change the base. If you want to use base 10, this comes down to log 10, log b, sorry. My eraser doesn't work. Let me see. Okay, here. Now it works. ln b, log b over log a. You can write it down like that. Or equivalently, you can do ln b over ln a too, okay? So using this formula, you can convert this into something like log, okay, this number goes to the base, 35, and then this number comes here. Log 30 with base 35, okay? So you can either input this expression into your calculator or this expression into your calculator. You'll get the same answer anyway. So let me do ln 30 divided by ln 35. Then this is 0. Nearest hundredth, okay, 0.96. Okay. Okay, do the same thing for 55, 56, 57, 58, 59. Okay. I'll do one more out of these five. Let me do 59. Okay, 59. 2 to the power of negative 1 over 3 times x is equal to 10. So what am I gonna do? There's no option. It says use natural log. So I'll do ln on both sides. Okay, so I do this. Then this power should be brought in front of the log. So that's negative 1 over 3x ln 2 is equal to ln 10. So I'll leave x on the left-hand side and get rid of everything else by dividing each side by negative 1 over 3 ln 2. So then you end up with ln 10 over negative 1 over 3 ln 2. Okay? So let me put this into the calculator. This is same as, okay, this 3 is the denominator of the denominator, right? Then this becomes numerator, so that's negative 3 ln 10 over ln 2. So whichever way that you use doesn't really matter. It's going to give you the same answer. So anyway, let me put this into the calculator. So ln 10 divided by, okay, negative 1 over 3 is negative 9.97. All right. Let me move to the next block. Transformations. Let f of x is equal to e to the x. And for each function, describe the transformations from f to g. So we're going from this function, the exponential function, to gx. All right, so for 61, gx is 6 times e to the x plus 1. And I always keep saying, okay, this number 6 that is multiplied on the original function represents the vertical, what? In this case, this number is greater than 1. This represents vertical stretch. Okay? By factor of what? Factor of 6. And then this plus 1, plus or minus, always represents translation. In this case, this is vertical translation, or shift upward. Shift up by 1 unit. Okay? So y is equal to e to the x, the basic exponential function, is this. This point is 1, and I always say, okay, there you should pick one more point for your reference. Okay, when this is 1, this is e. If this is y equals e to the x. Now, what happens after this transformation? Okay, this point right there, which is 0, 1, gets vertically stretched. So in this case, you have to multiply this 6 to y coordinate. So this becomes 0, 6. And this was 1, e. Okay? You have to multiply 6 to the y coordinate. So this reference point becomes 1, 6e. And then you add 1. That's a shift up by 1, so you have to add 1 to the y coordinate. So eventually, this point becomes 0, 7 if you add 1 to 6. And if you add 1 to 6e, it becomes 1, 6e plus 1. So basically, what you're going to have is this, what? Exponential growth function, but it's vertically stretched and shifted 1 upward. In this case, one more thing that you have to notice is that there was a what? Horizontal asymptote here, which is y is equal to 0, but it does not change when you stretch it by what? Factor of 6, but it also gets shifted when you shift it up by 1. So this becomes what? Y equals 1 in the new graph. So what this means is that if you, okay, vertical stretch by a factor of 6 means you have to multiply 6 to y. But in this case, y is 0. So when you multiply 6 to 0, you still get 0. Okay? But if you add 1, it's a different story. Okay? 0 changes to 1. So anyway, y equals 1 is a new horizontal asymptote here, y equals 1. And then your graph is vertically stretched, so it's like this. And what's this point right there? It's no longer 0, 1, but this got transformed into 0, 7. So this is 7 now. And the reference point is 1, 6e plus 1. So when x is 1, you get a number which is 6e plus 1. So this point right there is 1, 6e plus 1. Okay? 62, same thing. This is almost same as 61. Let me do 63 because this is a little bit different. So for 63, you start from f of x, which is e to the x, and this goes to gx, which is 0.25 times e to the power of 4x plus 4. Let me factor out 4, okay? 4 times x plus 1. It's always a better idea to keep a coefficient of x as 1. So there's a reason, I'll tell you why. Okay, so factor out 4 like this. Now, what does each of these numbers represent? Okay, these numbers. Again, this number that is multiplied in front of the original function f of x represents, in this case, this is less than 1. So that represents vertical compression. It's not stretch, okay? Vertical compression, okay, by a factor of 0.25. How about this number right there? Okay, this is 4 times something that includes x with coefficient of 1. So in that case, any number that appears in front of x represents horizontal dilation. But this number in horizontal dilations, that's exact opposite of vertical stretch or compression, because I said when this number is greater than 1, that represents vertical stretch, but this is opposite for x. If this number is greater than 1, it's not stretch, but it means what? Compression, okay? So this number represents horizontal compression by a factor of not 4, but it's reciprocal, 1 over 4. So you have to always take a reciprocal of any number that appears in front of x. So if you take a reciprocal, it becomes a number that is less than 1. So that represents compression, okay? And what is this number? 1. That's x plus 1. Okay, x plus 1 represents shift, that's a horizontal translation. That's a shift left by 1. If it was x minus 1, it represents shift right by 1. But this is plus, so that's shift left by 1. So this 0.25 and 4 is multiplied to something. So we have to apply those first. And then this plus 1 has to be done last, okay? So we do the multiplication first and then plus. So let's try to graph this thing. Okay, again, fx is equal to e to the x is this exponential growth function. So this point is 0, 1, and the reference point that we're going to use is 1, e. Okay, so what's going to happen to these numbers? I mean, these points, these coordinates. First of all, I'm going to do vertical compression by a factor of 0.25. So you have to multiply this number to the y coordinate. So this point becomes 0, comma, multiply 0.25 to 1, so that's 0.25. And this coordinate becomes 1, comma, 0.25e. We also have horizontal compression by a factor of 1 over 4. So let's apply that. So that's a horizontal compression, so you have to multiply 1 over 4 to x coordinates, okay? So in this case, x is 0, so it does not change. It's still 0, comma, 0.25. Okay, this one becomes 1 over 4, which is 0.25. So that becomes 0.25, comma, 0.25e. So all the multiplications are done. So the only thing that's left over is the shift left by 1. Shift left by 1 means you have to subtract 1 from x. So eventually this coordinate becomes, okay, subtract 1 from x coordinate. So this becomes negative 1, comma, 0.25. And this one becomes, subtract 1 from here, that's negative 0.75, comma, 0.25e. There was this horizontal asymptote, which is y is equal to 0. But is there any change to this one? No. When you vertically compress this thing by 0.25, you try to what? Multiply 0.25 to y values here, but it's 0, so it's not going to change. It's still 0. When you do the horizontal compression by a factor of 1 over 4, you multiply 1 over 4 to x, but this number, 0, is not x, it's y, okay? So that has nothing to do with this number. And then you're shifting this thing by what? 1 to the left. If you shift the horizontal asymptote, that is still at y is equal to 0, okay, does not change anything, okay? If you shift it to the left by 1, it's still this line itself. So there's no change in horizontal asymptote. So the resulting graph is what? We have horizontal asymptote still here at y is equal to 0. And we're going to have, it's like horizontally compressed and vertically compressed. But it's going to still have exponential growth shape, okay? So we have to plot these 2 points. I mean, locate these 2 points. So negative 1, comma 0.25 would be somewhere over here. That's negative 1, so that's negative 1, comma 0.25. And the second reference point is at negative 0, comma 0.75, so it's like here. So this point right there must be negative 0, comma 0.75, comma 0.25e. So you don't have to draw the graph for this problems, but I just wanted to show you how things are done here when you're doing transformations. So you have to be able to track the transformations of each coordinate here, okay, by doing what I just did. Okay, try to do the same thing for 64. Okay, let's go to the next block. Okay, this is same thing, okay? The original graph is ln x. Remember the graph of ln x? ln x is inverse of e to the x. So e to the x was this, passing through 1 here. The inverse graph is always reflection across this line, which is y equals x. So If you reflect it, you get this kind of graph. That's basically log graph. That's one. So for 65, this 3 right there, this is multiplied to original function f of x itself, ln x. That's 3 times ln x. So that represents, let me write it down here. This represents vertical stretch. That's greater than 1, right? By a factor of 3. And this number right there, that's x plus 1. Plus or minus represents shift, okay? So x plus 1 means shift left by 1. So you vertically stretch this thing. So you're going to have something like this. So it's like stretching this graph this way and this way. So you end up with this one. And then on top of that, we're shifting it to the left by 1. So this point 1 comes over to here. So this dotted line would come here like this. Okay, for this blue log graph, there was a vertical asymptote here. That was the vertical asymptote, which is x equals 0. But when you are shifting it to the left by 1, this also shifts to the left. So the new vertical asymptote will be at x is equal to -1. So the resulting graph would look like this. You have a vertical asymptote here at x equals -1, and then the log graph passes through the origin like this. For log graph, there's a reference point too. Okay, if this is what? That's 1, 0. And let's pick the second point over here. When this x is e, the y value would be 1. That's e, 1. That's the exact opposite of the exponential function. In exponential functions, we picked the second reference point at 1, e. Since natural log is what? Inverse of the exponential function e to the x, we switch x and y, then we get this. Okay, xy, which is 1, e, becomes e, 1. So if you apply these transformations, okay, how does this thing transform? First of all, when you do the vertical stretch by a factor of 3, you multiply that 3 to y, so it becomes e, 3. Now, when you shift this thing to the left by 1, you subtract 1, okay, from what? The x coordinate. So this becomes e minus 1, 3. Okay, this point right there, 1, 0, when you vertically stretch it by 3, you multiply 3 to the y coordinate, but y is 0, so it's still 1, 0. Now, when you shift it to the left by 1, you subtract 1 from the x coordinate. So this x coordinate is 0, it becomes 0, and y is still 0. So you have these 2 points as reference point on the new graph. So this is the first reference point, which is 0, 0. The second reference point would be somewhere over here, which is e minus 1, 3. Again, e is like 2.7, so when you subtract 1, that's almost 1.7. So that is e minus 1, and that is 3. Okay. Try to do the same thing for 66. Remember that when you multiply a negative number, it represents two things. That's a vertical stretch by a factor of 2, and at the same time, you flip it, okay, over the what? X-axis. That represents reflection over the x-axis. So remember that when you're doing 66. Okay, so when you're doing 67, this number in front of x represents what? Whenever you find a number in front of x, you take a reciprocal, 1 over 5. So you are multiplying 1 over 5 to x coordinates. So that represents horizontal compression, okay? Remember that when you're doing that. And this negative 2 represents vertical translation. You shift it down, okay? That's a shift down by 2. Okay, shift down by 2. Okay. All right. I'm gonna stop it for now. Let's say this is part one of 6.6 and 6.7. So I'm gonna upload another video for part 2, okay? So do this thing first.